Translating theoretical system design into a functional database requires forcing human-readable semantic concepts to collapse into a rigid architecture of flat tables. We handle this by using two distinct logical abstractions. First, the entity relationship, or ER model, maps the logical interactions of a real-world enterprise. Second, the relational model dictates the physical two-dimensional structure where the data actually lives. Moving from the abstract ER model to the physical relational model follows a strict deterministic reduction governed by algorithmic rules. The absolute baseline rule of this algorithm is simple. Every individual entity set and relationship set in the conceptual ER design must resolve to a unique relation schema. Adhering to this deterministic mathematical mapping prevents data anomalies and preserves structural integrity when the database is finally compiled. The foundational unit of this mapping is the strong entity set, an entity that exists entirely independently within the database logic. This standard visual notation for a strong entity contains a title, simple attributes, and a designated primary key. The mapping algorithm generates a single relational schema with distinct attributes. The physically underlined attribute translates directly into the primary key of the new table. Consider a user's birth date. Calculating their exact age produces a derived attribute. The rule is these are entirely ignored during schema generation. Because they calculate dynamically at runtime, they do not get a column in the permanent table. Following these steps, strong entities form the independent foundational tables of the database architecture. They require no external references or dependencies to exist. The first major stress test to the one-to-one mapping rule occurs when we introduce a multi-valued attribute. In the standard notation, a multi-valued attribute is enclosed in curly brackets. Take an instructor entity. It has a primary key ID, but it also tracks a multi-valued phone number attribute because an instructor might have both an office and a mobile number. The naive mapping approach fails here. Attempting to cram an array of multiple phone numbers into a single relational table cell violates first normal form, which requires atomic, indivisible data values. To solve this, the compiler generates a completely new, separate relation schema, exclusively to handle the multi-valued attribute. The first column contains the raw multi-valued data, the phone numbers. To maintain referential integrity, this new table also inherits its parent's primary key. Every individual phone number now resolves to a mathematically unique tuple, or row, in this secondary table, pairing the ID with one specific phone number. This creates a specific architectural edge case optimization. If an entity consists only of a primary key and a multi-valued attribute, like a time slot with an ID and multiple meeting times, the optimization rule is to completely drop the parent schema. Since the new secondary table already contains both the ID and the data, keeping the original single-column parent table is redundant. Extracting multi-valued attributes into distinct schemas enforces the atomic data limits of the relational model, while successfully preserving one-to-many semantic relationships. We next move to the most complex structural dependency in ER design, the weak entity set. A weak entity is a dataset whose existence is strictly dependent on an identifying strong entity. For example, a specific class section cannot exist without depending entirely on a parent course. Standard notation marks a weak entity with a double rectangle, a double diamond identifying relationship, and a dashed underline for its discriminator attribute. The double line indicates total participation, a many-to-one relationship towards its identifying strong entity. First, the weak entity populates a new table with its simple attributes. Since its discriminator attribute lacks a sufficient primary key, the table extracts and appends the primary key from its strong entity. The official primary key becomes the mathematical union of both. Appending this external key introduces the final architectural requirement, a foreign key constraint. This constraint strictly enforces that any row in the weak entities table must reference a valid pre-existing primary key in the strong entities table. Mapping weak entities translates a philosophical existence dependency into an unbreakable mathematical constraint. Looking at the final output of the deterministic reduction across these three scenarios, we see a complete structural blueprint.
The invisible connective tissue binding this relational architecture together consists of the generated foreign keys. Primary keys guarantee absolute tuple uniqueness within a flat, two-dimensional structure. Foreign keys strictly enforce the real-world semantic dependencies that were initially mapped in the abstract ER diagram. By applying this strict algorithmic translation, we replace subjective design guesswork with mathematical certainty. If the enterprise schema is rigorously designed at the conceptual ER level, the resulting relational tables will inherently align with database logic. This upfront conceptual precision drastically reduces or entirely eliminates the need for complex post-generation database normalization. Mastering this deterministic reduction empowers engineers to build scalable data architectures that perfectly mirror complex real-world logic without ever sacrificing structural integrity.